Okay, hello everyone. Welcome back. This video is a bit of an off-topic video, but I just wanted to, record this video to share what I've done. So this is my interpretation of linear regression, which is pretty common, and you probably know about it already. I just wanted to create the same type of problem and model and also create the steps for a machine learning problem, such as loading the data, training, validating, and also inference. So in order to do that, I created my own classes that I've used in my code, and I just wanted to share it with you guys. We are going to run each cell one by one, and also I'm going to explain to you what each cell does. And we are also going to look the class that I created here, the classes that I used, so we can also understand the implementation behind all the objects that we use. So these are the imports that I have. So this is this section here includes all my user-defined classes that I have created. In this video, I will be talking about two custom classes. One is linear regression, our model, and the second is the trainer class. I will also explain what each of them does, what each of them do. And these are other important libraries. We need to import Torch, of course, and also we import some data utilities: tensor dataset, DataLoader, and random split. You might kind of guess what these are used for. And also there's some libraries and some settings that I have here for plotting. So let's run this first, import our libraries and also our settings that we created. So this next cell is the constants that we're going to use throughout the video. The first one is our device, of course. We're going to use our CUDA device, my dedicated GPU on my laptop. The second one is data type. I created this constant because I didn't want to write torch float 32 over and over again. The next constant is batch size, which is currently 32, and also number of epochs is defined as well, which is 25. And also we have size constant, which is 200. This is going to be how many data points. This is going to represent how many data points I have in my data set that I'm going to generate. And also there is a generator class. This makes sure that we generate the same data set or the same split each time that we run the script. And our seed is 42. So this is mostly used in random processes. Because I use random module in order to create the data set, I am setting this generator to this to make sure that we have the same data set all the time. And also, I think I didn't really include the generator here. So let's also include our generator here. I forgot to do that. Let's also add this here. So let's also run this and see the output. So I've printed the current device and its name. So as you can see, I'm using some sort of a GPU. This is actually my dedicated GPU on my laptop, which is not the latest, but it's gonna suffice. So now we moved on to the dataset creation section. First, I have created data point X, which is randomly generated with size of 2 by size of 200 width by 2. This 2 is how many features we have. So in this example, we will be working with 2 features. Our data type is data type. Device is CPU now, because I'm going to plot the data first. So if I just write here my device, it's gonna be on my GPU, and I need to use like a CPU here. I didn't want to do that. And also we have our generator. Again, this makes sure that we are generating the same numbers each time. So in order to have a target that will have a linear relationship between our data points, I created using a linear function. So again, because we have two features, we have two weights here. The weight for the first feature is 2. The weight for the second feature is 3. These are important because we're going to use them in the later part of the video. So let's actually write this down, 2 and 3. And our bias, you probably can guess that it's 5. So I'm also going to write 5 here. And this is the next section here is just the noise that I added in order to kind of make it more realistic. Its multiplier is quite small, so it's not going to really affect the performance of our model that much. So let's create our data. So this section prints out x and y on a graph. So also it uses scatter function for this because they are each data points. And also I'm going to plot each feature on top of each other. So this is the feature that it generated. As you can see, our data clearly has a linear type of relationship. We can also kind of draw the line by ourselves, but we are not going to do that. We're going to let our model do that. Let's also print the x and its shape. So this is our data. As you can see, we have two features in the form of columns. And as you can see, the size is 200 by 2 because that's how we set 2 here in this line. Let's also print the shape of y. This is the y and its shape. As you can see, it has only the shape of 200 because we just only have one target for two features. So now we need to turn these tensors into data set. We do this operation with using tensor dataset class. As you can see, this is a dataset wrapping tensors. So we are going to wrap our tensors into a dataset with this. And I'm also going to print out the .tensors attribute of the data that we have created. So this puts out a form of a tuple. The first element is x and the second element is y. So that's what we did essentially here. With using tensor dataset, we created tuple that is consisting of x and y. Okay. So let's also create our model, but first let's check its implementation first in base.py. So as you can see, this is the linear regression class that I've created, which inherits from .module from torch.nn. You have to use this in order to create any type of model in PyTorch. There is some doc strings here and there. Don't worry about them. The most important thing here is the initialization and also the forward method. And there's just only two methods here, so both of them are important. As you can see, we have two inputs, two arguments here in initialization. The first is in dimensions, and the second is out dimensions. So out dimensions is default to 1. As you can see, this also explains the in dimensions is number of input features we have, and the out dimension is number of output features we have. This is going to be 1 because we are using linear regression. And this is usually 1 for basic regression as well. And also it says it here. So we use super to, for inheritance. I'm not going to talk about this. So these are our parameters. As you know, we have two parameters in case of linear regression, our weights and biases. In order to register these attributes as a parameter, we use an n parameter wrapper. This makes sure that we are creating a kind of tensor that is to be considered a module parameter. So with this, we can construct a compute graph and also compute their gradient and have some sort of back propagation attached to it. We are first initializing these both parameters with random. But as you can see, the shapes are different. Our weights are in the shape of in dimensions to out dimensions. This makes sense because weights should match the in dimensions. And we generate bias in the shape of out dimensions. In our case, this is going to be just 1. We simply are creating just a single scalar value for bias. And for both of them, we set requires grad to true because we want to calculate the gradient for these for both of these parameters in order to back propagate and also improve the loss. Okay, so the forward method is just forward pass. This defines the forward pass for our model. As you know, in linear regression, we use a simple formula for this. This is matrix multiplication between input and the weight, and bias added on top of the result. So this is what we are returning here. We are using matmul for this, and multiply x and w matrices to each other and adding the bias on top of it to get the target, to get the y. Okay, so this is what we are essentially doing here. So our model has input dimensions of 2 because that's how we created our data x, and we are also moving this model into our device because we're going to train it, and we want to make sure that we are using parallelization and also the speed up from our CUDA device. So next step, we need to create our data loaders. But first, we need to split our data into training and validation data. That's what we do here. There is a random split function that randomly splits a dataset into non-overlapping new datasets of given lengths. And this is the percentage of data to be split. The 80% of the data is going to be training data and 20% is going to be the validation data. And again, we are using the data class, data object that we've created previously. And also we are setting generator to generator because we want to make sure that each time these trained data and validation data datasets are the same. And correspond to these new subsets, we want to create loaders for both of these objects. That's what we do here. We are using DataLoader class. This is important because we want to load our data in batches and with respect to epoch size. So that's what we do here. As you can see, we input our data, the subsets of data that we previously created, and also inputting the batch size that we also previously created, and setting the shuffle to true because we want it to shuffle their data. So we are kind of preventing a sequential relationship between each data point. So I'm going to run this. So next part, I also created a trainer class. This encapsulates all the training processes that we need to define. This is a bit of a messy code, and usually this doesn't really change. So I'm going to just show it to you for a little bit. So this is the main training loop we have. This is for each epoch. As you can see, this is epoch, and in each epoch we are loading our batches with respect to the batch size. So this, what it does is this just forward passes the data to our model and gets the predictions and calculates the loss, and optimizer calculates the gradients and the backward propagation, and also it steps into the opposite side of the gradient, so it improves. And also I added few print statements here and there in order to follow along with the updated parameter values. So to make sure that everything works correctly. There's also some, calculation of total loss, average loss, and I also created here 2 dictionaries that's gonna store the average loss at each epoch. So that's what I do. I just use epoch as a key and storing the average loss for that epoch. And also we validate the results after each epoch as well. So we are also going to get a validation error as well. Okay, so this might be kind of complicated, but it just encapsulates the training the operations. We input our model. We input 2 data loaders that we've created. We also have our optimizer. In this case, we are using stochastic gradient descent. But because we are using batch size more than 1, this is going to be mini batch stochastic gradient descent. We are using our parameters as inputs, and we are using learning rate of 0.1. As a loss, as a criterion, we are using L1 loss, and I think this is mean absolute error. So we are, in order to have for criterion, we use mean absolute error, and we are using reduction to mean because we want to calculate its average. Okay, and also we are setting our device parameter to our device. This makes sure that each parameter that we are working with is on the same device. Okay, so I've run this. So let's this function, train function, is going to just train the model. And as you remember, these are the two dictionaries that I've created. These are the return arguments that we have for the train function. So this is going to train our model. So it's done. When we look at here, we can see each update for each epoch. So for first epoch, we have the loss of 7. But when we move on with the epochs, we can see that the loss is decreasing at each epoch. So as you can see, at the last epoch, we have quite a low loss. So this model is trained. So let's plot the losses for each epoch, both of the losses. So this is the loss at each epoch. As you can see, both of the losses are decreasing in between like 20 to first to 20th epoch, and then it settles down and it's quite small. As you can see, it's almost 0. So as you remember, we created the labels based on some sort of linear formula here, and I told you that we have two weights, which are 2 to 3, and then we have bias of 5. So let's check how close we got in terms of trained weights and biases. So this tells us that we have two weights, which the first one is 2.007, which is again pretty close to 2, which was the real value of the weight, and the second weight is 3.01, which is again pretty close to the real value, which is 3. The bias we got is 5.009. Again, this is pretty close to the real bias value, which was 5, which is 5 again. So our model is quite correct and it's quite accurate because the predicted weights and biases are quite close to the real values. And we can also say this because we got a quite a small loss. So you can also calculate the weights that we have with analytical approach. But in order to do this, we need to first add the bias term as a matrix, as a vector in our future matrix, and this is going to be called design matrix also. That's what we do here. We create a new x, which is just concatenation of bias and the older x. So let's you know what, let's also plot new x here. As you can see, this is a new x. So we have additional column here, which is the bias that I talked about, but we initialized it into 1, okay? So this is the new feature matrix, which is now called design matrix, because this also includes the bias and also each feature for each data point. So after we do that, we can calculate weight with this formula. I'm not going to talk about this formula in detail, but when I run this, I will get a result. So if we do not create any model and just calculate the weight that we want to have, the predicted weights will be not predicted, but the resulting weights will be 1.997, which is pretty close to 2. The second weight will be 3.007. Again, this is pretty close. And the bias that we will get will be 4.996. Again, this is pretty close to the real values. So again, you can also calculate the weight values, which is going to be weight and also the bias. So these are all the parameters we have. Again, you can get quite a good result. But in our system, the noise is not that effective. So if the noise was higher, this might be not as perfect. So let's, in order to create our model, in order to plot our model, I wanted to create some sort of a new axis, new tensor, that I can use it as an input and get the result. So I can plot the line that forms our model. In order to do that, I create a new tensor T using linspace. With parameters min and max, because this makes sure that we are covering all the data points with the size. And again, I use data type of float32 and reshaped it into the shape the compatible shape for my model. And because we need to generate this for both of the features, I concatenate it with itself to create a new t. This is a bit complicated. I don't want to really waste my time here. So in here, we are using inference, which means that we are just getting the prediction values without training our model. In order to do this, we use torch no grad. This makes sure that we are doing operations without calculating any gradient, which means that we are not gonna train our model. So we forward pass the tensor t into our model and get a prediction result of yt. So let's print both of these. Again, because we concatenated t with each other, both of the features are the same. Again, we are using t for just plotting purposes. And we will get a corresponding target values yt here. And these are going to be in the correct shape. As you can see, t is in the shape of 200 by 2, which is correct. And we also have corresponding target values in the shape of 200, which is again what we want. So lastly, I want to plot the generated data again, but also the predicted linear model that we come up with after training. And when I run this code, we get a quite nice graph here. So as you can see, this is this black line here is our linear model. And based on what I'm seeing here, I can say that we have successfully captured the linear relationship between the features and the target, because when you look at it, this makes sense, right? So that's the end of the video. That's what I really worked on, and I wanted to show it to you guys. Maybe you can, get something from this. Maybe you will be, inspired to recreate this result. I am also open to different interpretations and implementations of this code. I would be happy to see. Thank you for listening. That's it for the video. I hope to see you soon. Take care.